Physics 2212, Lab 4, Circuits by Nick Schweiker. Introduction, Principles, Purpose, and Results. The purpose of this lab is to initially predict the properties of circuits containing various resistors and capacitors, and then using multimeters to determine important current values and potential differences. Important physics concepts are the loop rule, the node rule, Ohm's law, resistors and capacitors in series versus parallel, conservation of energy and charge. Preview of the results is actual values closely matched predictions. Current in an RC circuit is exponentially time dependent. We used a real circuit in part one, so the data collected matches real life. Visualizations will be screenshots from the digital circuit model. For part two, utilize the same digital circuit model, which assumes that the resistance of the wire and the ammeter can be ignored. Assumptions are that the resistance of the wires and the ammeter is negligible. EMF equals delta V capacitor plus delta V resistors. So the system in this situation is all the components in the circuit. The surroundings is nothing. Initial conditions are no current or voltage through the circuit. Predictions I1 equals I2, REQ equals 147 ohms, I equals 0.02 amps, actual readings 0.019 amps. And then one ammeter is replaced with a voltmeter where delta V is 3 volts, I equals 0 amps because it is an open circuit. Experiment off to the left, you can see potential differences throughout the loop. V all around is the 3 volts of the batteries, and then you go through all the components, and then that leaves you with 0.2 volts that are unaccounted for, and the loop predicts, of course, 0 volts. That is likely due to the wires. Current is 20 milliamps, same as expected. Ammeter reading doesn't change because the voltmeter has high resistance, so little current flow, so loop with voltmeter can be ignored. Experiment. We connect the ammeter in parallel with the 100 ohm resistor. Current readings increases to 57 milliamps because less current passes through the higher 100 ohm resistor. When current splits at the node, some goes through the ammeter with no resistance. R47 equals 46 ohms. R of 100 equals 96 ohms. R wire is 0 ohms. R of ammeter is also 0 ohms due to the assumption we make. There is a flaw in the voltmeter readings where the round trip potential difference is supposed to be 0 volts, but it was actually 0.2 because the calculation is flawed. Setup 10 ohm for setup for part two, 10 ohm bulb, 20 ohm bulb, 9 volt battery, and 20 millifarad capacitor. Battery connected to the 10 ohm bulb and capacitor in series. Bulb starts brighten and then it dims until it goes out, which is the charging. The current decreases from the max it will be to 0 amps, and then when you disconnect the battery, the bulb lights up again and then dims until going out, which is the discharging. Current decreases from the max to 0 amps. For the 10 ohm bulb, it was 11 seconds to charge, 12 discharge. For 20 ohm bulb, 17 seconds to charge, 22.3 to discharge. If you want to take a look at the data observations, just pause it and you can look at the data chart and or data table in the graph. The main observations for a 9 volt battery, 200 millifarad capacitor, and 30 ohm light bulb. For the slope, we got negative 0.1668 in the experimental setup, and that would give us 6 seconds. And then the expected RC was also 6 seconds. So discussion, differences between model and reality. Part one, there are no differences because the data is real. Part two, certain components like the ammeter and the wire have small resistance, but are treated as if they don't have any. Potential source of error is also the voltmeter and the ammeter readings aren't perfect, so the data could be slightly skewed depending on tuning of each tool. For the what if questions, for the first one, by using an actual ammeter, there would be a slight discrepancy in the data because there would actually be some resistance. This would affect the circuits by decreasing the current flowing through the following components. I used the virtual circuit to model this. Time to charge would increase using a real ammeter compared to an idealized one. For the second what if question, if you're doing this lab with real circuit components, then you would use ammeter to measure the amount of time the capacitor takes to charge up compared to when you directly charge up the battery. So for the conclusion, there is a large difference between a simulated circuit compared to a real life one. Capacitors can be used as a pseudo timer to decrease the current over time. The node rule and loop rule are very important tools when observing and analyzing circuit behavior.